Hi everyone, I'm Julia, the chemistry tutor, and today I'm going to talk about balancing chemical reactions or equations. We call them reactions or equations. So we're going to balance them, and all that means is making sure we have the same number of every element on the reactant side as we have on the product side. That's conservation of mass. Okay, so whatever mass of elements goes into the reactants, that mass of elements has to come back out of the products. Okay, so we have to balance those, and those are what we're going to work on today. I'm going to start with a few of them that in the last video, when I talked about types of reactions, I'm going to use some of those and balance those reactions that I did. Okay, so if we have magnesium and oxygen, okay, so first of all, what type of a reaction is that? I have two things on the left, and it's an element and an element. The only thing that you can do with those is to put them together. We're going to combine them in a combination reaction. Okay, so that's our combination reaction. Okay, so we need to make sure we have the same number of magnesiums and oxygens on the reactants as the products. So one way we can do this is we can do a chart where we say our reactants and our products. We have magnesiums and we have oxygens. On the reactant side, we have one magnesium and two oxygens. On the products, so remember, these are reactants over here. These react to produce our products. Oops. Okay, so on the product side, I have one magnesium and one oxygen. So I need more oxygens on the product side, right? So if I multiply that times 2, I have to put the 2 in front. I cannot put a 2 behind it because magnesium's a +2 and oxygen's a -2. In our correct formula, we only need one oxygen for that whole thing to equal 0. Okay, so we do not carry that subscript with us. The only subscript we carry are ones that are part of polyatomic ions. We'll get to those in a little bit, okay? So we did not carry the 2 with us because we know from our nomenclature that our formula of magnesium oxide is MgO, not MgO2. Okay, so what do we need to do? We need to multiply those oxygens on the product by 2 by putting a 2 in front. But that also multiplied our magnesium times 2, right? So now we need to multiply our magnesium times 2 on the reactant side in order to get our 2 magnesiums. Okay, so you can use a chart like that to do it. And it's always a good idea to do that when you're starting, but it's time consuming. It takes a lot of time. And so when you're taking an exam, you don't want to be spending that kind of time on drawing the chart and doing all of this. So eventually you want to move past doing the chart. And we're going to move past it in this video. Okay, I'm going to help you move past that. Okay, so let's do another one. Let's do the potassium chloride plus oxygen. Okay, so that combines, it's another combination because I have two things on the left. They're combining to make one thing on the right. Okay, and you'll know this, we'll probably tell you what those products are. But know if you're reacting just like a metal, nonmetal with oxygen, you're probably making the chlorate or bromate or sulfate okay, so you're probably making one of those polyatomic ions. Okay, so if we were to do our reactants products here, we have potassiums, chlorines, and oxygens. On the reactant side, one potassium, one chlorine, two oxygens. On the product side, one potassium, one chlorine, three oxygens. Okay, so this is a trick that we do in chemistry, okay, where we balance diatomics last, which happened to work out here. So diatomics, remember, two of the same element, so oxygen is a diatomic. We always balance those last, because if you get an odd number on one side, and an even number on the other side, and it doesn't matter. Your even number could be here on your reactants and your odd number on your products. It doesn't matter. If you have an even number on one side and the diet of the diatomic and an odd number on the other, you double everything except the diatomic, and then you go back and fix the diatomic. Okay. Double everything, then go back and fix. Okay. So if we double everything, if we double our potassiums and we double our chlorides on both sides, so I put a 2 in front of here and a 2 in front of here. Okay. Oh, before I did that, I forgot to talk about the odd even, right? We have the even here and odd here for our oxygens. Okay. So I'm going to double everything but the diatomic. That's why we want to do those first, is because they're already balanced. So when I double them, they're still balanced. I still have the same number on both sides. Okay, but now I have 6 oxygens over here. 2 of this entire thing gives me 6, right? If I had 2 of these, I have 6 oxygens there. Okay, so now I have 6, so now I can just put a 3 in front of my O2, showing that I have 6 oxygens on that side now. Okay, so basically then what we did was we had to multiply that one times 3, and that one got multiplied by 2 when we multiplied the potassium and the chloride. Okay. Okay, so let's do mercury oxide. Okay, so if I had this one, okay, it's only at one thing over there on the left. You only have one thing. All you can do is break it apart, decompose it. So my mercury and my oxygen, and we know oxygen is a diatomic, so we have to put the 2 on there. Okay, and I don't feel like this one needs a chart. Let's try it without the chart. I have 1 mercury, 1 mercury. I have 2 oxygens. I need 2 oxygens, so I put a 2 in the front, and that gave me 2 mercuries, so I'll put a 2 in front of mercury. Okay, if I did the chart, I have mercury and I have oxygen. On the reactant side, I had 1 and 1, and on the product side, I had 1 and 2. So we know we need to multiply that by 2, which multiplies that by 2. So now we need to multiply that by 2 in order to make it even, in order to make it balanced. Okay. All right, so let's do, oh, here's a tough one to do. Okay, so let's do, oh, I forgot to put my triangle in there. Got to have that triangle there for the heat, right? Okay, so now if we're taking sodium bicarbonate, right, whose common name is baking soda, okay, and we heat it to decompose, it is going to make sodium carbonate, and it is going to make carbonic acid, okay? But that carbonic acid always breaks apart into water and carbon dioxide. Okay. So I'm going to sidebar for just a quick second over here. So these are your unstable acids that always, always, always break apart. Oh, not always acids. So these are the unstable ones that you need to know break apart. And they always break apart into water and what's left after water. Okay. So those, if you get those as products, you need to break them apart. Okay, it's when they're products, they're unstable as products. Okay. So we'll always be breaking those apart into water and what's left, okay? And the most common ones are probably your carbonic acid and your ammonium hydroxide. And this one you probably know, if you've ever used ammonia for cleaning, it's got an extremely strong smell because as soon as you open the bottle, it starts decomposing into water and ammonia gas. This is a gas, and that's a really strong smell, okay? All right, so when I'm doing this, okay, if I do my reactants and my products, I have sodiums, hydrogens, carbons, and oxygens. Okay, so I have on the left reactants, I have 1 sodium, 1 hydrogen, 1 carbon, 3 oxygens. And on the products, I have 2 sodiums, 2 carbons, right? Those 2 carbons. And I have 6, 7, oh, sorry, 3, 4, 5, 6 oxygens. Oh, sorry, 2 carbons, 6 oxygens. Okay. So the numbers are all kinds of crazy, right? Like I'm going to have to multiply all kinds of stuff in order to do this. Okay. So I'm just going to start with the sodium. Okay. So if I multiply my sodium times 2, that multiplies everything over here times 2. Because I put a 2 in front, that multiplies everything by 2. Okay, so now I have, let me write them like this. So I have 2, 2, 2, and 6. And so my sodiums and my hydrogens and my carbons match up. Oh, and look, my oxygens match up. That's all I had to do. Just put a 2 in front of the sodium. Okay, so and that would have been the same thing had we put a 2 in front of the hydrogen. It would have, right? If we had chosen any of those to double any of those on the reactant side, it would have automatically fixed the product side. Okay? All right, so let's look at another one. Let's look at, oh, here we go. Let's look at magnesium oxide and oxygen gas, okay? So this one, right, I have 2 things on the left, and they're going to combine to make 1 thing on the right, our combination reaction, okay? So if we do our reactants and our products, and you might be able to see this just right now looking at it, okay? I've got 1 magnesium. Oh, sorry, this should be CO2 here. Sorry about that. I need a carbon there because I have a carbon on the products. You can't get products that don't go in. Okay, so 1 carbon and 3 oxygens. And on the products, I have 1 magnesium, 1 carbon, 3 oxygens. It's already balanced. Okay, so if you can see it's already balanced, you don't even need to do the chart. It's already balanced. It's 1, 1, 1. You don't need to do anything with that. Okay, so let's look at, oh, here, let's look at a double replacement reaction. Okay, so let's look at magnesium phosphate. Okay. So from our nomenclature, magnesium's a +2 and phosphate's a -3. So if we swap and drop, I need the 3 magnesiums, right? If we bring the 3 down and 2 phosphates. Okay. Okay, so if I have magnesium phosphate reacting with sodium sulfate. Okay. So what type of a reaction do we have? Well, I have an ionic compound and an ionic compound, right? A metal, nonmetal, a metal, nonmetal. That's always a double replacement reaction. They are just going to switch partners. My magnesium hooks up with my sulfate. My sodium hooks up with my phosphate. So magnesium hooks up with sulfate and sodium hooks up with phosphate. Okay. So what I want you to notice is I did not bring that 3 with me on the magnesium. I did not bring that 2 with me on the phosphate, and I did not bring that 2 with me on the sodium. But I did bring the 4 on the phosphate and the 4 on the sulfate, because those are part of polyatomic ions. Those are families. Do not rip a family apart unless we tell you to. Okay, so the only subscripts, the small numbers at the bottom that you carry with you to the product side, are part of polyatomic ions that you've memorized. Okay, so let me get rid of all of those weird little circles there, all those colors, so we can see what's going on here. Okay, so when we're balancing equations, so our steps are, we determine what our products are. Okay, and that's based upon your type of reaction. Rxn means reaction. Then you need to make sure your formulas are correct. Okay, because if your formulas are not correct, that's all based on your nomenclature. If your formulas are not correct, either you will not be able to get it balanced or your balancing will be wrong. Okay, and then the last thing you do is balance the atoms on both sides to make sure you have the same number on both sides. Okay, so balancing those atoms on both sides. Okay. So what we do is we got our products based on our type of reaction. We said it's a double replacement reaction. So we switched partners, magnesium hooked up with sulfate and sodium hooked up with phosphate. Okay. So now we need to do step 2 and make sure our formulas are correct. Okay, so we know these we already did. We said magnesium's +2, phosphate's -3, sulfate's -2, sodium's +1. Excuse me. So those formulas are correct on the reactant side. So on the product side, I have a +2 and a -2 for magnesium and sulfate. So that already equals 0. That's a correct formula. Sodium's the +1, phosphate's the -3. So I'm going to swap and drop those. So I need 1 phosphate and 3 sodiums. Remember, we just swap it down. Okay. So I need 3 sodiums. Okay, so if we do our chart here, and I'm going to erase these because we don't actually put charges on compounds, right? Compounds equals 0 charge. Okay, so now I am going to look at, if I look at my reactants and my products, I have magnesiums, whoops, it's too close there. Magnesiums, phosphates, so we keep those polyatomic ions together as an entire family. Don't rip those apart. It's a whole lot easier to balance if you don't look at them separately. Okay, I have sodiums and I have phosphates. Okay. Oh, I am going to sidebar up here. On this one that I did, you saw that I did my carbons and my oxygens separately, even though that's a polyatomic. The reason is because it's not a polyatomic right there with the CO2. It changed. If it is different on the reactant and product side, you have to count them separately, like as carbons and oxygens, like I did here. Okay? But here, my polyatomic ions are the same on both sides, phosphate and phosphate, sulfate and sulfate. So I don't need to count them separately. I can just count them as what they are. And sorry, that should be sulfate, not phosphate. Okay, so I have on the reactant side 3 magnesiums, 2 phosphates, 2 sodiums, and 1 sulfate, right? That 4 is the part of the family. That's one of that family. Okay, and on the product side, I have 1 magnesium, 1 sulfate, 3 sodiums, and 1 phosphate. Okay, so again, we've got all kinds of numbers going on here. So we just have to choose. So I'm going to choose the first one. I need to multiply this magnesium times 3 in order to make my magnesiums correct. So I'm going to do that. And that gave me 3 sulfates. So that multiplied my sulfate times 3, right? Okay. But that messed up this sulfate. Now I need 3 sulfates over there. So I need to multiply that times 3. Okay, which means I need to put a 3 in front of the sodium sulfate over there. Oops. Okay, well, by putting a 3 in front of that sodium sulfate, it also multiplied my sodium times 3. So now I need to multiply the sodium on the product by 2 by putting a 2 in front of there. And that multiplied my phosphate times 2. So now I've got 3 magnesiums, 2 phosphates, 6 sodiums, and 3 sulfates. Okay. So I am going to remove these numbers and I'm going to show you how I do it without the chart. Because you saw how confusing that can be. Like, oh, I need to multiply this by this, but that multiplies that by that. So now I need to go back and multiply this by this, and that multiplies that by that. And so it can get kind of confusing. So the way I balance equations is I start with the one that has the most stuff in it. And in this case, it happens to be my first compound there. It could be a compound over on the product side. It doesn't matter if you start with the reactants or products. It doesn't matter if you start with the first compound, the second compound. It doesn't matter which one you start with, okay? I choose the one that has the most stuff in it, and magnesium phosphate has the most stuff. So I say, okay, I have 3 magnesiums here. So I'm going to put a 3 in front of my magnesium here. I'm going to stick with where I started. I did magnesium. Now I'm going to do phosphate. I have 2 phosphates here and 1 over here. So I'm going to put a 2 in front of that. So now my magnesiums and my phosphates are balanced. Okay, so now I'm going to move here. I have 2 sodiums here, and now I have 6 over here. So I'm going to put a 3 in front of that to give me 6 sodiums. And that gave me 3 sulfates. And I have 3 sulfates. Balanced, done. Okay, so if you start with the one that has the most stuff in it, everything else kind of balances itself out along the way. Okay, so let's see. Let's do another one of these. So what if I did one that I did earlier where I did copper 1 phosphate. And wait, what was that? Oh, ammonium acetate. Okay, so again, I have an ionic compound and an ionic compound. So it's just a double replacement reaction. Copper is going to hook up with acetate, ammonium with phosphate. So my copper hooks up with my acetate, and my ammonium hooks up with my phosphate. Okay. So you notice I did not bring the 3 from the copper because that's not a polyatomic ion, but I did bring the 4, the 4, the 2, the 3, the 2, right? I brought all of those because those are part of polyatomic ions. Okay. So let me get rid of some of that so we can see what's going on here. Okay, so I'm going to do it the way that I do it. Rather than doing that chart, I'm going to do it the way that I do it. Okay, so I feel like again, oh wait, I didn't make sure my formulas were true. Sorry about that. So over here, copper is a 1 because phosphate's a -3, right? If we swap those up the other direction, right? There's 1 phosphate. Okay, so I have copper 1, and in double replacement reactions, it's the same on the other side. Copper is a 1, and acetate is a -1. So that formula is correct. That formula is good. Okay, my ammonium is +1, and my phosphate's -3. So if I swap those, I bring my 3 to my phosphate, right, and my 1 to my ammonia. My 3 to my ammonium, and my 1 to my phosphate. So I need 3 ammoniums. Okay. So now that I have my correct formulas, so I determined what my products are based on my type of reaction. I made sure my formulas were correct. Now I'm going to balance my atoms on both sides. Okay, I feel like the ammonium phosphate in this case has the most stuff in it. Okay, so it could be the copper phosphate, it could be the ammonium phosphate. Either way, right? This one has 4 ions. That one has 2 ions. That one has 2 ions. And that one has 4 ions. Okay, so I'm going to start with the ammonium phosphate because he's got the most stuff in him, the most ions. Okay, so I have 3 ammoniums here. So I'm going to put a 3 in front of my ammonium on the other side. Okay, I'm going to stick with where I am. I've got 1 phosphate here, and I've got 1 phosphate here. So I'm good there. Okay, so since we started over here on the products, we are going to finish over there on the products. Don't suddenly jump over to the other side, okay? Don't suddenly start jumping around. Be very, very organized about this. Okay, so since I started on the products, I'm going to finish on the products. So I have 1 copper here, and I have 3 coppers here. So I'm going to put a 3 in front of my copper acetate on the product side. And that gave me 3 acetates, right? 3 of those. And I have 3 acetates here. Okay. So if we just start with the one that has the most stuff in it, everything kind of balances itself out along the way. Okay. I'm going to do an acid-base reaction, right? The special kind of double replacement. So I'm going to react phosphoric acid with magnesium hydroxide. Okay. So double replacement reaction, I have an ionic compound and an ionic compound. So they're just going to switch partners, right? There are swingers. So hydrogen hooks up with OH and magnesium hooks up with phosphate. So I'm going to put my magnesium with my phosphate and my H with my OH. Notice I did not bring the 3 from the hydrogen over there because that's not a polyatomic ion. I did not bring the 2 from the hydroxide because that is not part of that polyatomic ion. Okay, I did bring the 4 from the phosphate because that is part of the polyatomic ion. Okay, so now when we go to balance this, I feel like either the magnesium hydroxide or the phosphoric acid. I mean, I guess this one has 4 ions and that one has 3. Oh, I didn't make sure my formulas were correct. See? Don't make that mistake. So your magnesium is a +2 and your phosphate is a -3. So if we swap those down, I need 3 magnesiums and 2 phosphates. And water is water. Okay, HOH as water. And we're going to leave the HOH as water because it's easier to balance that way. We are going to balance our H's from our acid and our OH's from our base. Okay, we're going to balance those as H's and OH's, not as H's and O's. Okay, so I'm going to start with my phosphoric acid. So I have 3 hydrogens there. So I'm going to put a 3 in front of my water to give myself 3 hydrogens. Okay, we started with phosphoric acid, so I have 1 phosphate, and here I have, oh, I don't know why I started with phosphoric acid. The magnesium phosphate definitely has more stuff in it. Okay, so I'm going to start over on that. I'm going to remove that 3. Okay, we're going to start with magnesium phosphate. So he's got 3 magnesiums, and I've got 1 here, so I'm going to put a 3 in front of the magnesium hydroxide to give me 3 magnesiums. I started here, so I've got 2 phosphates here, so I'm going to put a 2 in front of my phosphoric acid to give me 2 phosphates. Okay, Since I started on the products, I am going to finish on the products. Don't suddenly pop over to the reactants, okay? So here I've got 1 hydrogen, and here I've got 6 hydrogens. So I'm going to put a 6 in front of the water. That gave me 6 hydroxides, and I have right here 6 hydroxides, right? We multiply the coefficient in the front. This is your coefficient by the subscript in the back. Oh, spelled that wrong. By the subscript in the back, okay? So what I want you to notice is I did not multiply this 2 times that 4, because that 4 is part of the polyatomic ion. Okay, that is 2 of the whole thing. You're multiplying 2 times 1 polyatomic ion. Okay, so that's our balance, right? When we start with the one that has the most stuff in it, everything else balances itself out along the way. Okay, so this was, we wanted to see water as HOH there because it's easier to balance. So I'm going to talk about the 2 times you want to see water as HOH. Okay, the 2 times that you see water as HOH in balancing equations. So 2 times that you want water to be HOH for balancing, because it's going to make it a whole lot easier, is the one that we just looked at, which is an acid plus a base. Always makes the salt and water. As you saw, so much easier to balance when we saw it as H's and OH's. Okay, it makes it much harder to balance when you're doing them as H's and O's separately. Okay, the other time is when you have a single replacement reaction. I'll use the abbreviation. So your single replacement reaction, when you have like metal, basically here, let me do this. So a metal plus water always makes a metal hydroxide and hydrogen gas. So again, we'll balance them as H's and OH's. So let me show you an example of that. So if I had magnesium reacting with water, oh, single replacement reaction, right? Single replacement reaction. So let's go double check this. So the magnesium is going to kick out the H. Okay, and so we have, oh, really? So I can't write on that right now, but magnesium is right there. Okay, so we've got magnesium is 1, 2, 3, 4, 5, 6, 7, 8 down. And hydrogen is way down here. So magnesium is definitely stronger than hydrogen. So it'll kick out the hydrogen. So magnesium kicks out the hydrogen and hooks up with the hydroxide. We know hydrogen is H2 as a gas. It's diatomic, right? And magnesium is a +2, hydroxide's a -1. So when we swap that, we get 2 hydroxides. Okay, and so we're going to do that water as H's and OH's. My H's and my OH's. Okay, so I'll start with magnesium hydroxide. It's got the most stuff in it. I've got 1 magnesium, 1 magnesium. I have 2 hydroxides, so I'll put a 2 in front of water to give me the 2 hydroxides. I started over here, so I'm going to finish over here. I have 2 hydrogens, and I have 2 hydrogens. I'm balanced. Okay, so it's much easier to balance it as H's and OH's. So those are the 2 times when you have an acid plus a base and when you have a metal plus water. Okay, otherwise, water is H2O. Easier to balance is H2O. But an acid plus a base, HOH, a metal plus water, HOH. Okay, so let's do a couple more balancing. So let's see what I did here. So I've got a combination reaction, I've got a decomposition, another decomposition, another combination. I have a double replacement, acid base, single replacement. All right, let's do another single replacement. What if I had aluminum reacting with copper 2 nitrate? Okay, so I said copper was a 2, nitrate's a -1, so that's where I got that formula. Okay, so now my aluminum is going to kick out the copper and hook up with the nitrate if aluminum's stronger than copper. Okay, so here, okay, I fixed my writing thing. So we are looking at, is aluminum stronger than copper? Okay, so copper is down here under hydrogen, right? He's a coinage metal. So he's under hydrogen. So there's copper. And here's my magnesium. So magnesium is definitely stronger than copper. I mean, aluminum. Ooh, I'm sorry, guys. I'm looking at aluminum, not magnesium. So let's try that again. So aluminum is right here. So again, aluminum is above copper. So aluminum is definitely stronger than copper. So the reaction is going to happen. So aluminum is going to take the nitrate and kick copper out by itself. Okay, so looking at our process, right? 1 is your products. We got our products based on our type of reaction. 2 is making sure our formulas are correct. Okay, so we did that over here. Over on the products, I've got a +3 and a -1. So if I swap those, I get 3 nitrates and 1 aluminum. Okay, so don't make the mistake and think that since you have a 3 right here that you're good. No, that is 1 nitrate. That 3 is part of the nitrate. You need 3 of that entire family. Okay. Okay, so we got our formulas correct because copper is just copper. Now we're going to balance the atoms. Okay. So I'm going to start with aluminum nitrate because he's got the most stuff in him. And if you look, I have 1 aluminum, 1 copper, 1 copper. So it's the nitrates that I need to think about, right? And I've got the 3 and the 2. So I don't know if it makes sense to you that we need a 3 in front of here to give us 6 nitrates and a 2 here to give us 6 nitrates. Okay, I'll stop that, right? I have the odd number, even number, but this is not a diatomic. Okay. However, we could do it like a diatomic. Everything else is already balanced. Okay, because that's the key. Everything else is already balanced. I have the even and the odd. So double everything I've already done, except those nitrates. Okay, so I doubled my copper and my aluminum. Okay, so now I need to come back and fix my copper and my aluminum. Okay, so now that gave me 6 nitrates, and that gave me 6 nitrates. Okay. Oh, that cannot be true. Hold on. Because that's just 2, 2, 2 of everything. 2, 2, 6. Oh, here's my problem. Look at that. I need a 3 there in order to give me 6 nitrates. Whew, I knew something seemed wrong there. Because you can't have the same number in front of all of them. If I had 2, 2, 2, 2, it's the same as 1, 1, 1, 1. Okay, and it didn't balance at 1, 1, 1, 1, so I knew 2, 2, 2, 2 was not correct. Okay, and that's where I made my mistake. I needed to multiply my 3 times my 2 to get 6, and my 2 times my 3 to get 6. Okay. Okay, so now I'm going to move to So we've done a single replacement, double replacement, decomposition, combination. Okay, so now I am going to do combustion. Okay, so combustion reactions have a few little things that you need to worry about in them. Okay, so remember combustion reactions are carbons, hydrogens, oxygens, sometimes oxygens. Oxygen gas, you always get oxygen gas. I'm going to start putting states in. I'm going to go back and look at states in a minute on all of these. So you always get carbon dioxide is a gas. You have to heat this. So the water that you get is also a gas because when you heat water, it's a gas. Okay. So remember that's our combustion reaction. So if I have my C3H6, nope, I'm just going to do C3H8 right now. Okay, so that's my propane, and that is a gas. Oxygen is always a gas. I need to heat this for it to happen. Carbon dioxide is a gas, and water is a gas. Okay, so remember, you always get carbon dioxide and water as products. Okay, and so remember, we do diatomics last, so our oxygen is going to be the last thing we balance. Okay, so we're going to do carbons and hydrogens first. So I have 3 carbons here, 3 carbons here. 8 hydrogens, so if I put a 4 in front of here, right, that gives me 8 hydrogens. Okay, so now I come check my oxygens. So I count, don't forget, you have oxygens in 2 places over here. You have oxygens here and here. So 3 times 2, I have 6 oxygens. 4 times 1, I have 4, so I have 10 oxygens over here. So I can just put a 5 in front of my O2, and I'm balanced. Done, good to go. Nothing special about it. Okay. Now, what if I do, sorry, I have a paper here I'm going to look at. So what if I were to do C8H18? Okay, so remember I talked about that this creates a lot of energy. So like propane, when you burn it, it creates all the energy to cook your food. This is octane. This would be the gasoline that you put in your car. Okay, so combustion is O2 gas and octane is a liquid. We have to heat this or give it a spark. We're always going to create carbon dioxide gas and water gas, water vapor. Okay. So we're going to start with the carbon. I have 8 carbons here, so I'm going to put 8 in front of my carbon dioxide. 18 hydrogens, so a 9 in front of my water gives me 18 hydrogens. So now when I count, I have 16 oxygens here and 9 oxygens there. So I have 25 oxygens. Okay, so here's where I have the odd number and the even number of oxygens. Okay, so now we go back and we double everything we've already done, everything except that diatomic. Okay, so we had a 1 in front of our octane, so I'm going to change that to a 2. I'll change my 8 to a 16 and my 9 to an 18. Okay, so I multiplied times 2. Okay, so you see it kept everything balanced. I have 16 carbons, 16 carbons. I have 2 times 18, I have 36 hydrogens. 2 times 18, I have 36 hydrogens. Okay, so my carbons and hydrogens stay balanced. That's why we balance those first. Okay, so now when I go to count my oxygens, now I've doubled my oxygens. Now I have 32 here and 18 here, and that adds up to 50 because I doubled my oxygens. Okay. Okay. So now I just put the 25 right there. It's always going to be whatever that odd number was right there. That's going to be the number that goes in front of your diatomic because you doubled it over here. Now you're cutting it in half over here. Okay. So in combustion reactions, often you have to double and come back and fix your diatomic. Okay, so let's do another one. Let's look at one that has oxygens in it. Okay, so what if I had C3H6O? That one form of that is acetone. Okay, and it is a liquid. If I add oxygen gas and give it a spark, it's going to create carbon dioxide gas and water vapor, water gas. Okay, so you'll notice the difference now is this one has oxygen in the compound. So we have to take that into account when we look at our oxygens. Okay, so same process, carbon first. So 3 carbons. Hydrogen, if I put a 3 in front of water, I get my 6 hydrogens. So now I have 6 oxygens here, 3 here, so I have 9 oxygens. So you might be thinking, even odd. But no, you have 3 oxygens over here. You have odd, odd. Okay, you're not going to go doubling stuff immediately. Let's wait and see what's happening here. Okay, so basically we need 9 oxygens over here. We have, not counting our diatomic, we have that one right there. So I need 8 from the O2. So I just put a 4 in front of it. Now I have 9 oxygens on the reactants, 9 oxygens on the products. Okay, so when you have oxygen in your compound, subtract those first. Then count your diatomic, figure out your diatomic. Okay. Okay, so let's do a C2. No, let's do C2H6O. Okay, this is ethanol. Ethanol. So alcohol that you drink, this is how your body breaks it down. It is a liquid. If we have the oxygen that we're breathing into our body as we respirate, there's some heat going on in our body. There's actually enzymes in our body. This is an enzyme as opposed to fire. Okay. And we're going to get carbon dioxide and water. Gas. In your body, that might be a liquid, but we're going to call it a gas because it's under energy. Okay. So now I'm going to start with my carbons. I've got 2 carbons, 2 carbons. 6 hydrogens. So if I put a 3 in front of water, it gives me my 6 hydrogens. Okay, so 2 and 2 is 4, and 3, so I have 7 oxygens over here. Okay, but here again, you have odd and odd, not odd and even, because I have 3 oxygens over here. Okay, so remember, we need 7 over here. We have 1 in our compound, so we need 6 from the O2. So we're just going to put a 3. Okay. So we don't need to go through and do it. But what if I had C2H6O2? Okay. We're not going to worry about what that is. Okay. We're going to call it a liquid. Add our oxygen gas, add our heat, make our carbon dioxide gas and our water vapor gas. Okay, so 2 carbons, 2 carbons, 6 hydrogens, a 3 in front of water gives me 6. So here I have 4 and 3. So I have 7 total oxygens, okay? Well, here now I have the odd and even, so you're likely going to have to double something, okay? But first, let's take into account that we need 7 oxygens. We have 2 of them right there. Okay, so we need 5 from our O2. So yes, we have to go back and double everything because we still have the even. So we've still got the odd and the odd. Okay. So, odd and odd. Forget the odd even. I don't mean to go down that road right now. Okay, so I have 5 from O2, so I'm going to have to go back and double everything. So this was a 1, so we're going to double that to a 2, 4, 6. So you see we have 4 carbons, 12 hydrogens, 12 hydrogens. So we're still balanced on our carbons and hydrogens. Okay, but that doubled my oxygens here. Now I have 8 and 6. I have 14 oxygens here. Okay, but remember, we still need to subtract what we have in our compound. So I need now 14. I have, because I have 2 times 2, I have 4. So now I need 10 from my O2. So I just put a 5 in front of the O2. Okay, so when you get the odd number, even number, you got to go do some going back and doubling things. But if you have oxygen in your compound, subtract those first before you figure out what you need from your O2, before you decide to double and all of that. Okay, so we'll do one more. So in your body, when you eat glucose, which is C12H22O11. Okay, so, and that is, I don't know, it's a solid. If you haven't dissolved it in water, it's just sugar, right? That's sucrose. I'm not going to worry about the state of it. Oxygen is a gas. Add some kind of heat or an enzyme. Carbon dioxide gas and water, vapor gas. Okay, so I have 12 carbons here. So I'll put a 12 in front of my carbon dioxide. 22 hydrogens, so an 11 in front of my water gives me 22 hydrogens. Okay, so now I'll count my oxygens. I have 24, and here I have 11. So I have 35 oxygens, and over here I have 11 and 13. Okay, so I have 13 oxygens. I have the odd and the odd. Let's see what's going on here. So I need 35 oxygens. I have 11 oxygens from right there. So that means I need 24 from my O2. So 24, I'm going to put a 12 in front of my O2. I've got 24 oxygens. Okay. So when we eat sugar, we need to breathe oxygen. This is part of why we breathe. It's to break down our sugars and our carbohydrates and fats that we eat. This is why we have to breathe out carbon dioxide, is because eventually in the end it breaks down into carbon dioxide and water, part of why our bodies are so much water. Okay, so that's balancing equations. You can start with the little charts that we did, looking at reactants and products and multiplying and all of that. But eventually you want to move past that to save yourself time. So then you go to starting with the thing that has the most stuff in it. And wherever you started, like this one over here, I had started with a magnesium phosphate and did my magnesium and my phosphate. And then I just stayed over here and did my sodium and sulfate. Be very organized about it. Okay. Okay, so I am going to talk about states real quick. Let me pull up that other page. Actually, no, I've changed my mind. I'm going to do a separate video on just states, and it's going to be like 10, maybe 15 minutes long, but I'll do that on just states, and I'll probably do some balancing equations in there just to keep us practiced up. Okay, but the thing for balancing equations, balancing reactions, is these three things right here. Okay, I'm gonna move up here where I have the other info. Okay, so we are determining what our products are based on our type of reaction. We're making sure our formulas are correct based on our nomenclature. Then we balance the atoms on both sides. Okay, those are your steps for balancing equations. And I believe that, oh wait, let me just go back here and just recap this real quick to be sure. The 2 times you want to see water is HOH, is when you're reacting an acid with a base. Remember, acids have hydrogens in front and OHs in the back. Okay, and also when you're doing a single replacement reaction, when it's a metal plus water, those are the 2 times you want to see water as HOH because it makes it easier to balance. Okay, all right, so I do believe that is all I have to say about all of that. So have a great day and see you in my next video.